Hello students, welcome to the class. So today we'll do the theory part 10 of the chapter 6 equilibrium, in which we'll be covering section 6.11 of the NCERT. So this is the disclaimer. Now in this class our objective would be to learn about a very important topic, which is salt hydrolysis. We will try to calculate the pH of the salt. At the same time, you would be confused that if it is a salt, then it should have a neutral solution, it should form a neutral solution, but you will see that this salt solutions are not neutral at all. Yes, there are cases in which salt solutions are neutral, but in most of the cases you will see that there is a shift towards either acidic or basic side. If I talk about the specific sections of the NCERT that we are going to cover, then it would be section 6.11.9, in which the topic is hydrolysis of salt and pH of their solution. Further, we will do a problem on the same, which is problem number 6.25 of the NCERT. So let's begin with the topic. To understand this, first you have to know how does a salt dissociates in a solvent. So if you are dissolving a salt into water, then it dissociates into its constituent ions. We know it very well. Salt is a strong electrolyte and it will dissociate completely. After this dissociation, two cases can arise depending upon the nature of the ion that is being released upon dissociation. What are those cases? First case is they do not react with water, right? So your ion can react with water, and in that case only the pH changes. If it is not reacting at all, then the ion only hydrates, or you can say it is getting surrounded by the molecules of water due to its charge. Depending upon the charge, the part of the water will be attached to it. If the charge is negative, then the water's positive part, which is hydrogen, will be attached to the ion, and if the charge is positive, then the water's negative part, which is oxygen, it will be attached to the ion. So this is called as hydration. We'll talk about it in a detailed manner. Now talking about the case 2, in this case there is a change in pH, and this pH change occurs due to the reaction of that ion with water, and that process is called as hydrolysis. So you can say that in the first case your ion is getting hydrated, in the second case your ion is getting hydrolyzed, or you can simply say it is reacting with water. Let us look at the case 1, what happens to the ion specifically. So for that, we will say that whenever your ion does not react with water molecule, instead it is only getting surrounded by those water molecules in the solution, then we say that the process is called as hydration, means surrounding by the water molecule. Obviously, if it is getting surrounded, if no reaction is occurring, so we can say that ions are not reacting. As a result of that, your actual structure of the ion is not observed. You can say that that actual structure is hidden inside a shell, and that shell is created by the water which is surrounding your ion. We call this overall thing as hydration shell or hydration sphere. Now, can we take an example? Yes. So all the strong bases have contribution as cations to a salt. We know it very well that the cationic part in the salt is coming from the base and the anionic part is coming from the acid, right? So if the cation is of a strong base, then in that case the cation does not react. In place of that, it gets hydrated. Similarly, if it is an anion of a strong acid, then it is not reacting with your water molecule. In place of that, it is getting hydrated or getting surrounded by the water molecule to form the hydration sphere. So remember this, you will see hydration in case of ions coming from strong acids or strong bases. You got it? So it is very important line to remember that anions and cations of strong acids and strong bases are respectively showing hydration. Moving on to the case 2. So this was the first case, which is of hydration. The second case, which is of our interest, I would say, is the case of hydrolysis. So when the reaction is occurring between the cation or anion of a salt with water, then it produces acidic and basic medium respectively. Now we'll see that cation produces acidic medium or anion. So that will be a part of discussion when we'll see that thing with the help of example. But you must know that cation and anion react with water to produce either your acidic solution or your basic solution. Now, if it is reacting, then what it will form? So ions are what? They are conjugates of weak acids and weak bases. What is the meaning of this? We saw that in the previous case, the cations or anions were hydrated if and if only if they are a part of strong electrolytes. Here in this case, it will only hydrolyze if your ion is a part of weak electrolyte, which is weak acid or weak base. So we will illustrate both of these cases with the help of a specific example. So here we are taking a salt, which is sodium acetate. Now, in this sodium acetate, the acid which is involved in the formation of this salt is weak acid, and the base which is involved in the formation of salt is a strong base. How can we know it? Yeah, it's very simple. First, let's dissociate this ion. What you will get? You will get acetate ion and sodium ion. Now you know it very well that this acetate ion is nothing but a anion of the acetic acid, which is a weak acid. You can take any other acid which is releasing this anion, and in each case you will notice that your acid is a weak one. Similarly, if I talk about the sodium plus, then this cation is a what? This is a part of strong base. Now that strong base can be sodium hydroxide or any other strong base, but for sure it will be of a strong base. Now what will happen? First of all, if I talk about the sodium ion, then this sodium ion which is released in the water, it will, what will happen? It will just hydrate in water to form the sodium plus in the aqueous form. So in the first step, nothing is happening. You are dissociating your salt into sodium ion and your acetate ion. Now the sodium ion is reacting, or I would not say reacting, is getting hydrated with water to form the sodium plus, which is in the aqueous form. Is it clear? And why it is happening? Because sodium plus is nothing but a cation of a strong base like your sodium hydroxide, and that is the reason it is getting hydrated. Now what will happen to the acetate ion? Because in the dissociation, we are also getting the acetate ion. Now to consider this, we will see the happening that is occurring, right? So first of all, of course, your acetate ion will also get hydrated in the first part. So that is a part of the reaction. But it will not be remaining in that state. Like your sodium plus is remaining in the aqueous state, there is no further reaction. But in the case of acetate ion, once it is hydrated, it reacts further to form the acetic acid and the hydroxide ion. Now you know it very well that once it forms this acetic acid, the backward dissociation is not that much promoted due to the nature of this acid, which is a weak one. Got it? But one thing you are seeing here, which is the formation of hydroxide ion in this whole process. So when you are dissolving this sodium acetate, you are getting sodium plus, which is only getting hydrated and not disturbing the pH. But if you are looking at the reaction of this acetate ion, the first is getting hydrated, but along with it, it is producing your hydroxide ion due to reaction with water. And this increased hydroxide concentration will result in a basic solution. I hope you are now able to understand that how does a salt changes the pH from neutral to a basic one in this case, and you will see a case where it is converted to a acidic one as well. Got it? Now can you remember this thing? Is there a way to remember this thing? Yes. So whichever is a strong one, that will decide the pH. If your base is strong, then in that case, the salt which is formed will result in a basic solution due to hydrolysis. If the acid is strong, then in that case, your pH of the solution will be according to that acid, right? I hope you got my point. So, can we prepare a chart for all of these types? We have only seen a type where we have a salt of a weak acid and a strong base. Now, there are much more possibilities that we can consider. So, depending on the precursors, means the nature of the acid and base, we can have 4 types. What are those? First is of a salt of a strong acid and strong base. Second is salt of weak acid and strong base. Then we have salt of strong acid and weak base. And lastly, we have the salt of weak acid plus weak base. So these are the 4 conditions you can imagine by changing the combination of strong and weak according to the base and acid respectively. Our next task is to quantify this whole thing. We know it very well that if your acid is strong, then in that case we get an acidic solution. If your base is strong, we get a basic solution. But here is a third case also in which both are strong. We will look on to that, how the nature of the solution is decided. And we have a fourth case also where both of them are weak. So we'll look on to that also. But before moving on to that, we should know that how do we quantify it. So first we will start with the strong acid and strong base and see what is the nature of the solution that is being formed. So here are with the first case, strong acid and strong base. Now if I consider this strong acid and strong base, then one thing is for sure. What is it? That both of the cations and anions will come from strong base and strong acid respectively, right? And if they are coming from strong bases and strong acids, what you can think of? So we can decide this with the help of an example. Suppose we have this NaCl. Then this NaCl has 2 parts, cation, which is Na plus, and this is coming from a strong base like sodium hydroxide, and Cl minus, which is again coming from a strong acid like HCl. Now both of these ions, whether the strong base is cation or the strong acid anion, both will get hydrated. We know it very well. We have seen this. If the ions are coming from the strong electrolytes, they will get hydrolyzed. They will get hydrated and not hydrolyzed, right? So in this case, there is no such reaction or no such change in pH. Therefore, the solution is overall neutral and the pH is constrained to the 7 value. I hope you are clear about this first case. So what we have seen in this first case, that due to the nature of the cation and anion, which are coming from strong electrolytes, we are seeing only hydration of these ions and no hydrolysis. As a result, the solution is remaining neutral and there is no change in pH, which is kept to 7. Now we will move on to the second case. With this case only, I will try to quantify all of the hydrolysis case. You will do the same calculation for the remaining cases. I will help you with the second one and tell you the result of third and fourth. So for that, again, we are taking the example of hydrolysis of the sodium acetate. We know it very well. What will happen from the previous discussion? So it is a salt of a weak acid, acetic acid, and a strong base, which is sodium hydroxide. Now, this will dissociate completely to form the sodium plus ion and acetate minus ion. Talking about the acetate ion, this is the only part that will hydrolyze because sodium plus ion is a part of a strong base. Therefore, it will get hydrated and we are not interested in that. We are interested in the hydrolysis part. So what we will do? We will write the hydrolysis reaction. So this is your hydrolysis reaction. Acetate ion reacting with water to form the acetic acid and hydroxide. So what is hydrolysis? It is simply the reaction of your given ion with a water. Now, as a result of this reaction, of course, you will see the formation of a basic solution. Here you can see that the hydroxide ion is produced as an end result, and the acetic acid which is produced, it will remain in undissociated form and therefore will not affect the pH. So we can say that the hydrolysis of this acetate, sodium acetate, will result in a basic solution. But we need to quantify it further, as I said you earlier. How we'll quantify it? We will try to calculate the pH. In that process, our first step is to calculate the KH. What is KH? It is defined as the equilibrium constant for the hydrolysis reaction. So we have seen this hydrolysis reaction in the previous part. Now, if you write the equilibrium constant for this reaction, what you will get? You will get your KH. So KH can be written as concentration of acetic acid multiplied by the concentration of hydroxide ion divided by the concentration of acetate ion. Got it? Now this is a first quantification, which is hydrolysis constant. Moving on further, we will define a new term, which is relation between KH, KW and Ka. Remember, this relation is very, very important for you. How do we define it? We know it very well that the ionization constant of water is H3O plus concentration multiplied by the OH minus concentration. So this is the definition for Kw. Then what do we have for the dissociation constant? It is given by concentration of the hydronium ion or H plus ion multiplied by the concentration of acetate ion divided by the concentration of acetic acid. Now, the third term which we are interested in is the hydrolysis constant, and we have derived the equation for the hydrolysis constant in the previous slide. We will put that same thing here. So that will be acetic acid concentration multiplied by the hydroxide concentration divided by the acetate ion concentration. So this is your KH. Now, in the next step, we will take the product of KH and Ka, right? For the hydrolysis constant and dissociation constant, we will multiply them both. If you will do so, you will notice that the acetate ion and the acetic acid concentration is getting cancelled out, right? In this equation, if you consider, it is getting cancelled out, and we are finally getting H3O plus multiplied by OH minus, which can be written equals to the Kw. So this is the definition of Kw, and we have just put this here. So finally, we are getting a new relation between these three, which is KH multiplied by Ka gives you Kw. I hope this part is clear to you. Now moving on to the third part of this hydrolysis, which is degree of hydrolysis. Now this degree of hydrolysis is quite similar to the alpha thing. You know that alpha is nothing but the fraction of a electrolyte getting dissociated. If you are considering this same thing for the case of salt, right, then in that case we will tell it as degree of hydrolysis. How? Let us try to understand this thing. Say we have an initial concentration C, then we can represent this equilibrium attainment with the help of this given table. Initially we have C amount of acetate ion. Suppose H amount, I would say H fraction of salt is getting hydrolyzed. Therefore, the total salt which is getting hydrolyzed is CH, and we know that the equivalence of acetate ion and acetic acid is same in the equation. So if CH is getting hydrolyzed, that means CH will be produced, and hydroxide ion will also have a concentration as CH. Now what is the remaining concentration of the acetate ion if CH is getting hydrolyzed? It will be C minus CH. If I try to write the KH for the above table, how I will write it? So it will be CH multiplied by CH, means product concentration multiplied divided by the reactant's concentration. So in reactant we have water which is present in excess, so we will not consider it. We will only consider this acetate ion. Here I have taken C common, so we are writing it as C into 1 minus H. Now we will cut off this C from the numerator and the denominator. As a result, we will get our final equation as CH square by 1 minus H. Our further task is to keep this hydrolysis constant less than 1, and it is much more less than 1. Why it is so? Because this hydrolysis occurs only up to a small extent. Therefore, we can finally write KH is equals to CH square if we are ignoring H in comparison to 1. So this is your required equation for KH in terms of H. Now moving on further, our last part and the most important part is the pH calculation. How we'll do it? So here is your table for it, for the equilibrium condition. We know this table. Now to calculate the pH, first we will calculate the hydroxide ion concentration, which is equals to the CH. We can look at the table, and if you know the value of H, we saw that in the previous session, that in the previous slide, that H can be equals to root under KH by C. So we'll put that H value here, and if you just do this simple arithmetic calculation, you will get your OH minus concentration as root under KH into C. Obviously, this will be the case. Now, how we will define this POH? So that is nothing but negative logarithm of the OH minus concentration. So negative logarithm of root under KH into C. So this is your POH. But we are interested in the pH calculation. How we'll do it? Yeah, it's very simple. We'll just continue with the previous equation. We know that for pH calculation, we already know the POH. And we also know that pH is equals to pKw minus POH. So this is coming from the equation pKw is equals to pH plus POH. Further, if you put the value of POH, it will be plus log root under KH into C. Next, we are using this relation of KH, KW and Ka. We have seen this equation. We will put this in the place of KH, and finally we will get pH is equals to pKw plus log root under KW into C by Ka. Finally, we can just rearrange this equation and write it as pH is equals to pKw minus then half of minus log Kw. See, we have used an identity which is log A by log B is written as log A minus log B, and log A into log B is written as log A plus log B. If you just rearrange this equation, you will get the final relation as pH is equals to half pKw plus pKa plus log C. So this is your required equation. Can you do something again with this equation further? Yes. We can put the value of pKw, which is 14, and this will be true at 298 Kelvin, and in that case we can simply write it as 7 plus. So half of 14 will give you 7 plus then half pK plus log C, right? So you will use this form of equation in most of the cases rather than taking the pKw thing. You will put it as 14 and then use it for your calculation. Now we can try to write the similar equations for all categories of salt. What categories of salt? So we have seen it for the weak acid and strong base. We got KH is equals to KW by Ka, and H is equals to root under KW by Ka into C. What about pH? It will be half pKa plus log C. Moving on to the strong acid and weak base, what we can write about the nature? Since we have a strong acid, therefore the nature will be acidic, and the KH will be, instead of K, we will write it as Kb. So KW by Kb. What about H? So H is root under KH by C. If you put the value of KH here, you will get it as KW by Kb into C, right? And what about pH? So you can remember this in this way. We know that the nature of the first solution, which is weak acid and strong base, is a basic one. So the pH is greater than 7, so we are writing 7 plus, means greater than 7. If it is of a strong acid, that means the solution is acidic, so the pH will be less than 7, so we'll write 7 minus. I hope you are getting the tricky part here. Now moving on to the last situation, which is weak acid and weak base. In this case, we cannot define the absolute nature of the solution. For that, we have to look upon the specific acid and base and look upon their ionization constant value. If your acid have a greater ionization constant, that means your K is greater than Kb, then the solution will be acidic. If your K is less than Kb, then the solution will be basic, and if both are equal, that means it will be a neutral solution. For this case, your KH will be KW by Ka into B, and if you substitute this value for the H, which is root under KH by C, then in this case we don't have the C term, right? So if you define H for this weak acid and weak base, you will see that H is nothing but simply root under KH, and instead of KH, if you write KW by Ka into B, you got your H in terms of Kw, Ka and B. Finally, what would be the pH? It will be 7 plus half pKa minus pKb. Now you can look at the final equation and say that why we are having a acidic, basic and neutral solution. Suppose this pKa is greater, that means this whole value will be greater than 0 and 7 will be added with some positive value. So that will result in a what solution? That will result in a basic solution, right? Why I am saying that pKa is greater? So if your pKa is greater, that means your solution is having a smaller value of K and a greater value of Kb. Remember, K and Kb are inversely proportional to pK and pKb, right? So simply you can say that in case of weak acid and weak base, if your acid is stronger, that means your solution will be acidic. If your base is stronger, then your solution will be basic, and both if K and Kb value are equal, then the solution will be neutral in that case, because this right side term after the addition sign will be equals to 0. Now here is a question for you. It's a very simple one. You have to say that what will be the pH value for ammonium acetate solution if you are given with the pKa of acetic acid as 4.76 and pKb of ammonium hydroxide, which is 4.75. Your time to solve the question starts now. So it is directly related to the previous formulas that you have seen. First, you have to decide that whether this ammonium acetate is a salt of weak acid, strong base, or strong acid, strong base, or weak acid, weak base, or strong acid, strong base. So this is your first and the most important task. Once you do it, you will easily solve this question, because the next part is to just apply the formula. You have 5 more seconds to go. Okay, your time is up. Let's see how we can solve it. So first, what we will do, we will write what are the things that are given. We are given with the value of pKa of acetic acid, it is 4.76, then pKb 4.75, and when you want to calculate the pH, you know it very well that this ammonium cyanate is coming from ammonia and acetic acid. These both are considered as weak base and weak acid respectively, because ammonia is a weak base and acetic acid is also a weak acid. Therefore, what we can say, this is a salt of weak base and a weak acid, and we can apply the formula of pH is equals to 7 plus half pK minus half pKb. Just put the values here. You are already given with the values. You will get it as 7 plus half 4.76 minus 4.75. Further, 4.76 minus 4.75 will give you 0.01, and 7 plus half into 0.01 will give you your final value as 7.005. Got it? Now the part is that, can you see one thing, that the acetic acid is having a greater pKa value, which is 4.76, and it is of course greater than pKb. So from this part, it is very clear that Ka will be less than Kb, because pKa is greater than pKb. Now if we got this thing clear, then we can say that the solution will be of a basic nature, because the Kb value is greater, and hence we are getting the pH of the solution as 7.005. Although this deviation from the neutral part is very less, so it is appropriate to the amount of 0.005, but still it's a basic one. Let us try to summarize all of those which we have studied till now. So first, we have seen the first case of the salt, which is salt of strong acid and strong base, and we said that due to the nature of the cation and the anion, there is no hydrolysis, and the pH is equals to 7, which is a case of neutral. Second type which we saw was salt of weak acid and strong base. Remember, you have to decide the nature of the salt by looking at the precursors. If your precursor is having a strong base, your nature will be basic. If your precursor is having a strong acid, then your nature will be acidic. So here the base is strong, so the pH will be greater than 7 and the solution will be basic, and the ion which will get hydrolyzed will be the anion. Okay. Moving on to the next part, which is salt of strong acid and strong base. Here the cation will get hydrolyzed Similar to the previous case, you can just look at the equation of the hydrolysis. Remember, when we are taking a strong acid and a weak base, suppose we are taking ammonium as the what? As the cation, which is coming from ammonia. So this will get hydrolyzed and it will result in the production of H plus. So finally, you will get your solution as acidic, whose pH will be less than 7. Last, we saw the case of salt of weak acid and weak base. In this case, you cannot decide whether the solution is acidic or basic until and unless you have the value of pKa and pKb or Ka and Kb. So in this case, both of the cation and the anion will get hydrolyzed because both are coming from a weak acid and weak base. Further, the pH will depend upon the value of Ka and Kb. So if your Ka is greater, means the solution will be acidic. If your Kb is greater, then the solution will be basic. So this was all for today's class. I hope you enjoyed the session. Thank you for joining it.